Welcome back to your machine learning A to Z course. Super excited to have you back on board, and today we're kicking off the support vector regression intuition. Super pumped about these tutorials. Got some very exciting slides coming up for you. So what is support vector regression? Well, support vector regression was invented back in the 90s by Vladimir Vapnik and his colleagues who were working at the Bell Labs. At the time that was the AT&T Bell Labs. Now they're Nokia Bell Labs. And a lot of support vector machine and support vector regression are discussed in Vladimir Vapnik's book, The Nature of Statistical Learning, 1992. In this course, we will be covering both support vector machine in the part of the course to do with classification and support vector regression. We'll be talking about it here. And in addition to that, we'll also be talking about kernel support vector machine and kernel support vector regression and the kernel trick and many other things like that. So there's a lot of exciting tutorials on these topics. But for now, we're just going to limit ourselves to support vector regression, specifically linear support vector regression. So here we go. Here we've got two plots, and we need that in order to compare SVR to the simple linear regression. That will really help us understand things. So here on the left, we've got some random plots, random dots. I'm going to copy them over to the right, so we know that these are identical. There's no tricks involved. There's an absolutely identical, this is an absolutely identical set of data. And let's start with the one on the left. We're going to apply a simple linear regression. We've already discussed what it's like, but let's quickly refresh. So basically, we're going to have this line go through the data. And how is this line derived? Well, a method called the ordinary least squares method will be applied to find this line. Basically, we want to minimize the distance between the this value y, the actual value in the data, and y hat, basically what it would have been on a trend line. We take the difference here or difference here, we square it, and we want to minimize that. That's ordinary least squares method. Essentially what we're doing is minimizing the error. We want to have a line with the minimum error possible. So that's the intuition behind a simple linear regression, something we already talked about. Now, how does the support vector regression work? Well, let's have a look on the right. With SVR, instead of a simple line, you'll see a tube. And here you have the regression line in the middle, but then there's this tube around. And what does this tube do? Well, this tube has a width of epsilon, and the width is measured vertically. It's important along this axis, not perpendicular to the tube, but vertically. And this tube itself is called the epsilon insensitive tube. And what does that mean? Well, that means that any points in our dataset that fall inside the tube, they will be disregarding the error. So basically, this tube, think of it as a margin of error that we are allowing our model to have and not care about any error inside here. So any discrepancy between, or any like distance between this point over here and the line, as in like, for instance, here we could see, let's look at which point is that? That's 1, 2, 3. This third point, you can see the line is even different, right? The results can be different and probably will be different. So this third point here, there's a distance between the line here, and we care about this error. Here, we don't care about this error because it falls within this epsilon insensitive tube. So we're disregarding any kind of errors in here. And that's kind of the key behind support vector regression. It gives a little bit of movement, or a little bit of buffer to our model. And at the same time, we have points that are outside the epsilon insensitive tube. There they are. And for them, we do care about the error. And here it will be measured as the distance between the point and the tube itself. So not the trend line, but the tube itself. These distances have names. They're either xi star if the point is below the tube, or xi if the point is above the tube. And they're called, so these values xi are called slack variables. So it's either xi star if it's below, xi photo star if it's above. And we do care about the error, so we care about these distances. And the way we care about it, so we're going to try to avoid formulas. I will give additional reading, something you can look into further down at the end of this tutorial. But just for completeness sake, here is the formula. So in the case of OLS, it was a simple ordinary least squared like that. Here it's a bit more complex. We're not going to talk about this part over here, but what we're focusing on is this, and we can see that we're minimizing. We want these distances, the sum of these distances, to be minimal. Once again, there'll be additional reading at the end if you'd like to go into it, but effectively these points, the ones that are outside our tube, are dictating what the tube will look like, how the tube will be positioned. So the error within the tube is completely disregarded. We don't care about the error, unlike in the ordinary squared. So we're giving some kind of buffer of flexibility to our tube, or like allowing it to accounting for some kind of error that we might expect in the data. It's normal sometimes for there to be error, but these ones, they are important to us. And also, one final thing, why is this method called support vector regression? Well, because effectively these points, all of these points outside, any point actually, any point on this plot is a vector, right? Can be represented as a vector in this two-dimensional space, or a multi-dimensional space if you have more features. So in this case, it's can be represented by a two-dimensional vector. So they are all, these points are vectors, but the ones that we've highlighted in red, the ones outside the tube, they're the support vectors, because they are dictating how this tube is created. So basically they're supporting the structure or formation of this tube, and that's why they're called support vectors, and that's why this is a support vector regression. And so there we go, that's what it's all about. That's just important to remember, the epsilon insensitive tube, and that support vector regression just cares about the errors of anything that's lying outside this tube. And to finish off, as promised, here's the additional reading. So if you'd like to learn a bit more, have a look at Chapter 4, Support Vector Regression, in a book called Efficient Learning Machines, Theories, Concepts, and Applications for Engineers and System Design by Marietta Wad and Rahul Khanna. And here's a link here where it's aggregated on this portal for published work. Something you'll note that it might be a little bit confusing. Here they say these are potential support vectors. They are referring only to the ones close. I've had a look at different literature, and the literature I prefer is the one that says, in this respect, is the one that says that the support vectors are the ones that are outside, and they are outside basically any point outside the tube is a support vector. So that's how we discussed it inside this tutorial, but have a look at this different nomenclature. Maybe that'll be a good perspective to have a different view. But overall, the first couple of paragraphs describing the whole problem, they're very well written. I liked how they were written, and I think can be a valuable addition if you're looking for additional reading. So there we go, that's support vector regression. Hope you enjoyed this tutorial, and I look forward to seeing you next time. Until then, happy analyzing. Welcome back to your machine learning A to Z course. In this tutorial, I'd like to give you a quick heads up about the non-linear support vector regression. So what we discussed previously was intuition for SVR indeed, but this was intuition of the linear support vector regression model. And while it's a great start into the world of SVR, it is just a start. There is so much more to support vector regression. This was a simple linear model. There are actually other models. And rest assured, they will be covered in this course. So they are coming up, and we'll be talking about, for instance, the RBF kernel, SVR, and the kernel trick, and all these important things that make this model even more robust. However, I wanted to give you this heads up because already in the upcoming Python tutorials that are coming right after, just following this tutorial in this section, you'll be working with Adlan to create your first SVR model, and the SVR model will already be non-linear. So here you can see the results. Like, I've blurred them out on purpose because I wanted to make sure you don't get a spoiler by seeing the results in terms of the numbers. But you can see the model itself here, and you can see that it's non-linear. It's not just a straight line, and that is because we're using, or Adlan will be showing you how to use the radial basis function kernel for this SVR. So it's already going to be a non-linear SVR. So now what's the reason for this heads up? Well, the thing is that the non-linear support vector regression will be covered off further down the course beyond this section. So it's a bit of a mismatch, but that's done on purpose because that's the easier way to grasp these concepts. And I'll explain in this following slide. So this is what this is what the nonlinear SVR will look like, right? So compared to this is your linear model. As you can see, it's much more complex over here. We have to go into a third dimension and perform some calculations or some modeling there and go back. So it is quite involved. And in order to get there, the following tutorials are essential. So first, in the section on SVM, you'll find a tutorial called SVM Intuition. So that's an essential tutorial to take in the steps to getting to kernel SVR or nonlinear SVR. Then in the section on kernel SVM, the following section, you can find them in the part of the course that is to do with classification. So in the section on kernel SVM, there's a tutorial called kernel SVM Intuition. Then there's mapping to a higher dimension, the kernel trick, types of kernel function, and then finally non-linear kernel SVR. So as you can see, it's quite a complex topic, and it comes at the very end of this list. So from here you have two choices. You can either just after this tutorial go straight to Adlan's Python tutorials on kernel on SVR that are coming up and just do them, and just keep in mind that he's using a non-linear kernel and that will come later in the course. The intuition for it will come later in the course. Or if you would like to get the intuition before you do the practical side of things, then it's essential that you would need to go through all of these tutorials that are mentioned on this slide over here, get to nonlinear kernel SVR, and then come back to the Python tutorials. So there are two options. My preference, if you ask me, I would just go for Adlan's Python tutorials now. Just keep in mind that he's using a nonlinear kernel, follow along with the code, and then you will still get the intuition when the time is right, when you get to this section on kernel SVM. So there we go. That's just a quick heads up on what's coming up. Of course, the choice is yours, and in any case, please enjoy the course, and there's lots of fun tutorials coming up. And I look forward to seeing you in the next one. Until then, happy analyzing.
Hello my friends, and welcome to this new practical activity on, this time, support vector regression. So, I have to start by telling you that the model we're about to implement will be slightly more advanced than the models we built before. But it's totally fine, we will do it together and we will succeed 100%. So, why is it slightly more advanced? Well, that's because we will have to play a lot with feature scaling, and I can tell you that after this implementation of the SVR model, you will be a master in feature scaling, because you will know not only how to apply the feature scaling transformation, but also how to apply the inverse transformation, to go back to the original scaling. So you will know all the sub-tools, let's say, of feature scaling, and you will handle them like a pro. All right? So, if you're ready, let's start. And just before we go inside the folder, let's make sure here that we're all on the same page. I gave you the link to this folder, containing all the codes and datasets right before this tutorial and an article. So make sure to connect to it. And now we should all be on the same page. And therefore, we're going to go, of course, to part 2 regression. And then, of course, to support vector regression SVR. All right, and as usual, we're going to start with Python. So we're going to go to that Python folder, inside which you will find the same data set as before, because I would like to compare the performance of different regression models on this data set, which proved to have some nonlinear relationships, between the feature, which is the level, the position level going from 1 to 10, and the salary going from $45,000 to $1 million per year. So here again, this is exactly the same scenario. We want to train this time a support vector regression model to learn and understand the correlations between these position levels and these salaries. And to quickly remind the context, we are hiring a new person who is expecting a 160K salary, justifying this by the fact that this person earned a 160K salary in the previous company. This data is exactly the data of the previous company, with the different position levels from business analyst to CEO and their corresponding salary. And so not only we want to train a model to learn these relationships, but also we want to deploy this model to predict the salary that this person had in this previous company, knowing that indeed this person was a region manager for a couple of years and therefore is considered to have a position level of 6.5. So that's the exact same scenario, exact same data set. And so now let's build the support vector regression model on this data set to see if it performs better than the previous model, which showed great results, the polynomial regression model. All right, so let's do this. Let's close this and let's open our support vector regression implementation, either with Google Collaboratory if you love it, or with Jupyter Notebook, because indeed it is an IPYNB file. All right, so that's the whole implementation. Let me quickly show you the structure of the implementation. We're going to start by importing the libraries as usual, then importing the dataset, then applying feature scaling. So this is interesting. This time we have to apply feature scaling because in the SVR model there is not this, explicit equation of the dependent variable with respect to the features, and mostly they're not those, coefficients multiplying each of the features and therefore not compensating with lower values for the features taking high values. No, this time the support vector regression model has an implicit equation of, the dependent variable with respect to the features, so we don't have such coefficients, and we will definitely have to apply feature scaling for this model. So you see, you start to understand when and when not to apply feature scaling. Well, we don't have to apply feature scaling for linear regression models where you have indeed those coefficients that can compensate with the high values of the features. And so, of course, these include simple linear regression, multiple linear regression, and polynomial regression. And you will see later on in the course many other models. And for other models which usually have an implicit equation, an implicit relationship between the dependent variable y and the features x, well, usually for these models we have to apply feature scaling. All right? Then we will of course train the SVR model on the whole dataset. This time it's the same. We won't split the whole dataset into a training set and a test set because we want to leverage the maximum data to learn these correlations between those position levels and the salaries. So we won't do that split, and we will directly train the SVR model on the whole dataset. Then after this training, well, we'll have a smart SVR model, which therefore we're going to use to predict this new result and exactly that salary of this position level of 6.5, and we will compare, of course, that prediction with the prediction of the polynomial regression model, which I've kept here. And then, of course, we will visualize the SVR result in low resolution and high resolution to see, of course, the regression curve of the SVR model. All right, I'm sure you noticed that I did not click on each of these contents. Well, I did that on purpose. It's because I don't want to reveal the prediction, the predicted salary by the SVR model. I want us to save the surprise until, we execute that cell to return that predicted salary. All right, let's keep the suspense. And now, whenever you're ready, let's create a copy of this file because this one is in read-only mode, and therefore we want to create a copy in order to re-implement it from scratch together and make sure to focus because, this will be quite more advanced than before. So let's put that right here. And there we go. Now let's remove the cells and let's try not to look at the final results, right? You just put your eyes around here. You don't look at the results because let's try to keep the surprise of the predicted salary up to the end, up to the final execution of the code. All right, so let's remove all this and this as well, only the code cells, right? Please keep all the text cells so that we can keep the well-highlighted structure of this implementation. All right, and now really make sure to not look at the result, the output of the code cell, because that's where you will see, the final results. All right, I managed to do it. I did not look at it, even if, of course, I know the result. But what I mean is that it was totally possible not to look at it. All right, so that's the whole structure. Now we're ready to start this implementation. And so there you go. I suggest that we really tackle in a flashlight. I love saying this, I know, but we will tackle in 1 second that data preprocessing phase, except that part, because that part is actually not that direct. There are going to be some things to explain. All right, so let's do this. Let's start by importing the libraries. And of course, to do this, we're going to use our data preprocessing template. I hope you have it prepared. So there you go. Let's first get this code to import the libraries in a new code cell. Paste here. Then we're going to import the dataset. And actually, to do this, we'll get our polynomial regression implementation because, this is the exact same dataset. And we don't have to explain that again because you perfectly know and understand now how this works, right? And voila, that's the thing I wanted to do in 1 second. Now we're going to quickly upload the dataset in order to, execute this cell after this one, of course. So now it's connecting to a runtime to enable file browsing. And in a second, we should be able to see the upload button. Perfect. So upload. And then, as usual, we're going to go into our machine learning A to Z folder. I like to put it on my desktop, but find it wherever you put it on your computer. Then part 2 regression, then support vector regression, then Python. And there you go. That's the dataset. Open, and it will be uploaded inside the notebook. Perfect. All right, then we're going to execute these 2 cells and this one as well. All right, and perfect. Now we have the dataset. And now we're going to stop here for this tutorial, and we will tackle this next step, feature scaling, in the next one. And make sure to be prepared and ready to tackle this because we'll have a few things to do. It's not difficult, but just make sure to be focused for that next tutorial because I'm going to explain a new situation where you have to apply feature scaling in a certain way. So I'll see you in the next tutorial, and until then, enjoy machine learning. Hello my friends. All right, excellent. We already did the essentials with data preprocessing by importing the libraries and importing the dataset. And now I'd like us to particularly focus on this feature scaling that we're about to do. So I've already taught you feature scaling in the data preprocessing part, part 1, where indeed we implemented together this feature scaling tool at the very end, feature scaling, where we learned how to scale with standardization the training set and the test set separately. Okay, so that's what we did. Now we are in a slightly different situation in the sense that indeed we do not have a split of the data set between a training set and a test set. And that, I remind, is because we want to leverage the maximum data in order to learn the correlations between the position levels and the salaries. So the first thing is we will actually apply exceptionally feature scaling on the whole matrix of features X. Then the second important point and the second difference with what I taught you before in this same data preprocessing tools implementation is the fact that in this situation, we only applied feature scaling to the features, right? We only applied feature scaling to xtrain and xtest, which are the features of respectively the training set and the test set. And we did not apply feature scaling to the dependent variable vector y. But why was that? Why didn't we apply here feature scaling to the dependent variable vector y? Well, that's because remember, the data set for our data preprocessing tools implementation was a data set where the dependent variable was taking values 0 or 1, right? We can scroll up to have a look again. Remember, these were the purchased decisions of this retail company, and that's the dependent variable taking the following values: 0 for the customer didn't buy the product, and 1, the customer bought the product. And therefore, since it took value 0 or 1, then we did not have to apply feature scaling here, because exactly same as the dummy variables here, the values 0 and 1 are already in the same range as the one resulting from applying feature scaling onto the features. All right? But now we are in a different situation. Indeed, this is our new dataset, position salaries, where the features are indeed the levels going from 1 to 10, and the dependent variable taking values from 45,000 to 1 million. And so now I have a question for you, and after answering this question, you will know what to do in any feature scaling situation. So according to you, do we have to apply feature scaling to this dependent variable, the salary? And the answer is, well, yes. I'm sure you guessed that right. Indeed, we have to apply feature scaling because same, we don't want this feature, which takes values much lower than the values of the dependent variable, to be neglected by the SVR model. And that even if there is not an explicit equation, like in multiple linear regression, this is an explicit equation because y is explicitly resulting from a linear combination of the features. And for our SVR model, this is not the case. We have an implicit equation, but still, through this implicit equation, well, if the salary is way higher than the features, and here this is absolutely the case, well, accordingly, the feature might be neglected by the model. And actually, I of course tried to build this SVR model without applying feature scaling, and you can check that this absolutely doesn't work. Indeed, if we don't apply feature scaling for our SVR implementation and training on this dataset, well, you will see that the SVR model will not work at all. So we have to apply feature scaling here on both the feature, where the values go from 1 to 10, and the dependent variable taking values from 45,000 to 1 million. All right, and so now you know everything about feature scaling. You know what to do in any situation. You know that you don't apply feature scaling to some dummy variables resulting from one hot encoding. You know that when a dependent variable takes binary values like 0 and 1, you don't have to apply feature scaling either because the values are already in the right range. You also know that when the dependent variable takes super high values with respect to the other features, then you have to apply feature scaling to put all the features and the dependent variable in the same range. And finally, you also know that whenever you want to split your dataset into the training set and the test set, well, you have to apply feature scaling after the split. All right, so now you know everything about feature scaling, and by the end of this implementation, you will also know something very important to do with feature scaling, but you know, on the practical side, which will be the inverse transformation of feature scaling. You know, when you scale your features or your dependent variable, at some point, you know, to get the final prediction and to visualize the results, you need to inverse that feature scaling, you know, inverse that transformation to go back to the original scale. And I will, of course, teach you how to do it so that we can not only get a very relevant prediction at the end in this step here, and also a super nice visualization where indeed we have the x-axis and the y-axis back in their original scale. You know, these scales of the levels going from 1 to 10, and this scale of the salaries going from 45,000 to 1 million. All right, so you will know everything, and now let's implement this new step, feature scaling. But just before, since we're going to apply a lot of transformations on both x and y, well, we're going to do some print to see the before and after the transformation. All right, so let's create two new code cells here. Let's first do a print of the matrix of features x, then a print of the dependent variable vector y. Now we're going to run the cell to print x, and x contains, of course, in a 2D array, as you can see with a double pair of square brackets, all the position levels going from 1 to 10, so that was totally expected. Then let's print y, which will this time contain in a one-dimensional vector all the salaries corresponding to these position levels, so all good there. But now we will have to do a first transformation, and I'm not even talking about feature scaling. That first transformation will be to reshape this y into actually an array, you know, a two-dimensional array where you have the salaries displayed vertically. Meaning that instead of having, you know, a horizontal vector of the salaries here, well, we want to have the salaries vertically in a two-dimensional array. And so now the question is, why do we want y to have such a format, you know, in the 2D array? Well, that's because, you know, the standard scalar class that will perform standardization, meaning feature scaling, expects one unique format in its input, you know, when you apply the fit transform method, which is a 2D array. If you input here a one-dimensional vector like what we have here, this will return an error, simply because, well, this standard scalar class expects a 2D array as its input. So now we just have to transform this into a 2D array, and you actually know exactly how to do that because we already did it. I'll give you a hint, this was in the multiple linear regression section. And so now, well, of course, I would like you to press pause on this video and try to transform y, or, you know, reshape y into this 2D array with the salaries displayed vertically. All right, so please press pause, and now I'm going to give you the solution. All right, so we're going to create a new code cell to do this. And so, well, first we want to update y, and therefore, you know, we will start with this, y equals, and then we'll do the necessary transformation to return this new y. And so how do we do this? So the first thing to do is to take y again, from which we're going to call that reshape function, into which we're going to input, well, you know, the new shape that we would like y to have. And remember how we have to enter this new shape? Well, we have to input here two elements. The first one being the number of rows of this new y, this new format of y we want to have, and then the number of columns. So that's easy, since we want to have the salaries displayed vertically, in different rows actually. Well, what we want to have for the number of rows is, of course, len of y, the length of y, meaning the number of elements in y, meaning the number of salaries, okay? So that's the number of rows, and then the second element here is the number of columns, and of course we want one column because we want to display the salaries vertically in a 2D array, of course, and therefore here we input 1, as in one column. So we're going to have, actually, since we have 10 salaries, we're going to have 10 rows and one column. Okay, so it was good to do it again. Now you become more familiar with this reshape trick. Okay, and now of course we're going to print this to see and to check that everything's all right, and mostly that we have the right format expected by this standard scale class, which we'll use then to apply feature scaling. So there we go, print y, and let's first execute this to reshape y, and now let's print y to indeed check two things. That first we have a 2D array, we can clearly see that with the double pair of square brackets, and also the salaries displayed vertically, just like this matrix of features, which is also a 2D array, of course. Alright, so now everything's perfect, we're ready to apply feature scaling, and so we're going to do that right away, starting by creating a new code cell here. Alright. So now, how are we going to do this efficiently? We always want to be efficient when we code. So of course, we're going to grab our tool in our data preprocessing toolkit. I'm talking, of course, about the feature scaling tool, and we'll have to adapt this a bit because this was applied on the training and test sets, but no worries, we will adapt it very quickly and efficiently. So I'm copying this and I'm pasting that right here. And now, of course, I would like you to please press pause again and try to figure out on your own what we have to modify here to make this feature scaling work for our situation. All right, so pause, and now let me give you the solution. All right, so first we don't have a training set or test set here, so I'm going to remove this line of code. I'm going to, remove that as well, all the index selections and here as well, and I'm just keeping X, and then let's see what we have to do. All right, so first that's already more clean. Now, with what we have here, these 3 lines of code, we are indeed applying feature scaling to the matrix of features X, which is one of the things we have to do indeed. That's good. However, as we've just explained, we also have to scale the dependent variable vector, the salaries. And of course, and that's the important thing you had to understand and figure out, we're not going to use the same standard scalar object on both the matrix of features X and the dependent variable vector Y. Why is that? That's because, when you fit your object SC on your data, well, it is going to compute the mean and the standard deviation of that same variable, and therefore, since of course we don't have the same mean and same standard deviation for our levels here and our salaries, well, obviously we have to create 2 standard scalar objects, one that will be fitted to X in order to compute the mean and standard deviation of the position levels, and one that will be fitted to Y to indeed compute the mean and the standard deviation of the salaries. All right, so that was the only important thing to understand, and therefore here I'm actually going to call this SC object SCX in order to say that it's the scalar of the matrix of features X, and here SCX as well. And now I'm going to create a new standard scalar object, the one that will be used on our dependent variable vector Y, and therefore here I'm replacing SCX by, we're going to call it SCY, so that it's perfectly clear that this is the scalar of X and this is the scalar of Y. And now we're going to copy this, paste that right below, and here we'll just have 3 little replacements to do, which are first replacing X here by Y, then SCX here by SCY, and X here by Y. So that now we're ready to scale both our matrix of features X and our dependent variable vector Y. Let's check it out. Let's run this cell. And now we're going to add 2 new code cells to print the new X and the new Y and see what they have become. All right, so 2 new code cells. And let's start here with the print of x, good, and then a print of y. And now let's run these two cells here, starting with print x. And indeed, well, we have some perfectly scaled values of the position levels going from minus 1.5, and that corresponds, of course, to position level number 1, and 1.56, which corresponds to position level number 10. All right, and now let's print y, and this will be interesting. Here, the values will go from minus 0.7, which corresponds, of course, to the salary of $45,000 per year, and 2.64, which corresponds to the $1 million salary. And as you can see here, this time the values are in the range from -1 to +3. That's why in the data preprocessing part, I told you that usually standardization transform your values between -3 and +3. All right, so there you go. Congratulations. Now you successfully applied feature scaling for the SVR model, and especially for this data set where clearly feature scaling had to be applied on the dependent variable. And now I'm really glad for you because you now know how to handle any situation of feature scaling. You just need to know how to inverse the transformation, but that will come very quickly because then we will actually train the SVR model on the whole data set. And then when we get our smart model after the training, well, we will predict that salary of the position level number 6.5, and that's where you will learn how to inverse the transformation. All right, so I can't wait. Let's build and train first the SVR model on the whole data set, and then we'll get together the final results. And until then, enjoy machine learning. Hello my friends, welcome to this new tutorial, and now we're about to train the SVR model on the whole data set after a successful data preprocessing phase with your new experience in feature scaling, because now you can handle very well all the different situations. All right, so let's train that SVR model on the whole data set, of course, because we did not do a split of the data set between training and test sets. So there you go. Let's create a new code cell. And now let's build, of course, in the most efficient way, the SVR model. So we're going to build it with scikit-learn, of course. I remind that scikit-learn is the best data science library, excluding deep learning, because of course we have TensorFlow and PyTorch. But for any machine learning model that is not based on neural networks, well, scikit-learn is definitely by far the best data science library. And for what we are interested in right now, you know, the SVR model, well, we will build it with a class called SVR, as simple as that, which belongs to a module of scikit-learn called SVM. And so we have to start here from first scikit-learn to access the scikit-learn library, from which we're going to get access to that SVM module. So that's the module from which we're going to import that SVR class. Perfect. Now we have the class, and you of course know the next natural step. Anytime you import a class, the next natural step is of course to create an object or an instance of this class, and we're going to call that object regressor, just like before, because this instance or object of the SVR class is nothing else than the SVR regressor itself, you know, the support vector for regression regressor. So regressor, and then of course we are going to call this class SVR, add some parentheses, and this time we have to input a parameter. Because indeed, remember in the intuition lecture of support vector regression, and you will also see in the intuition lecture of the support vector machine in the next part, part 3 classification, well, you actually have what we call kernels, which can either learn some linear relationships, and that's the linear kernel, or nonlinear relationships in your dataset, which are the nonlinear kernels, such as the RBF radial basis. I will actually show it to you right away, you know. That's the Gaussian RBF kernel, which is given by this formula, and I can actually show you the plot of that kernel. Here it is. So that's the Gaussian RBF kernel. And then you also have some other kernels which I've prepared here on this great website showing clearly the different kernels of the support vector machine, but also the SVR, because the SVR is nothing else than a support vector machine model for regression. So let's see, here they are. There is the polynomial kernel, adapted for nonlinear datasets. You have the Gaussian kernel, which has the classic Gaussian function, then the Gaussian radial basis function, the most widely used one, and that's actually the one we will use. Then you have the Laplace one, the hyperbolic tangent kernel as well, that's a popular one. Sigmoid, well, you have all of them here. And so if you're curious, yes, you can have a look at them. but the one we will use for our implementation will be, and that's the one I recommend each time you experiment with an SVR model, and that's the radial basis function kernel, the RBF kernel. And that's exactly what we have to input here in our parameters. And so the name of that parameter is kernel, so that's the name of the parameter, and then the value we want for that parameter, which corresponds to the radial basis function, has the code name in quotes RBF. And that's it. That's only what we have to input here. So that basically creates the SVR model with the radial basis function kernel. And so now that means only one thing. That means that we already have built the model. We already have the SVR model itself. And so now the last final natural step is to, of course, train that regressor on the whole data set, right? Which is also the training set. Okay, so let's do this. You know exactly how to do this. From this point, it's exactly the same as before, the same function, which is of course the fit function, and which will train this SVR model on your whole data set, right? To learn the correlations between the position levels and the salaries, and all this done with the radial basis function kernel. All right, so let's do this. Let's train our regressor. So we take our regressor object first, and as usual, we add here a dot, and then the fit method, which takes as input this time not xtrain and ytrain, because we have not created a separate training set, but of course this time the whole data set, which remember was feature scaled, both on the matrix of features x part and the dependent variable y part. And so that's exactly what we have to input here, both x and y. And that's it. Congratulations, now you know how to build and train an SVR model after a successful data preprocessing phase, including a special feature scaling. Alright, and so now we have a very interesting next step. It is the step where we predict the new result, and I'm not saying this because I'm looking forward to seeing the result of the SVR prediction, compared to the polynomial regression prediction. No, what I mean is that this next step is very interesting because it will teach you how to reverse the scaling of your prediction. Because you will see that when we apply the predict method to predict this new result, well, it will be returned in the scale that was used for y, right? The new scale of y after it was transformed. And so we'll have to reverse this transformation, we'll have to reverse the scaling in order to get the original scale of y, and I will teach you exactly how to do it. Of course, you can try to do it on your own, by looking at the documentation, which method can do this, reverse the scaling, and if you figure it out, well, you should be able to predict that salary. But I'm warning you, it's not that direct, so there you go. As soon as you're ready, let's implement that solution in the next tutorial. And until then, enjoy machine learning. All right, here we go. Let's predict that salary with the SVR machine learning model. All right, so this time it's not going to be as easy as previously because we'll have to do some inverse transformation. I asked you to try to do it yourself, and now we're about to implement the solution together. All right, so let's do this. Let's start by creating a new code cell. And according to you now, what is the first step we have to do? It's very natural. Indeed, we want to predict a new result, so the natural idea that comes to mind is to call the predict method, from our SVR regressor object here. So let's do this. Let's first call, the regressor itself, because that's from this object that you have to call the predict method. And inside the parentheses, what we have to input. We have to input, of course, that position level of 6.5, right? Because this person we want to hire had a region manager position, but after a couple of years, so we consider it to be 6.5. And remember that this position level has to be in a 2D array, so we have to add here a double pair of square brackets, and inside input 6.5. So that was the original format, expected by the predict method of our previous machine learning models, including polynomial regression, okay? But as I told you, it's not that easy here because we did a lot of feature scaling and transformations on everything, the matrix of features x and the dependent variable vector y. So here we have to do some extra things. All right, so first thing, well, since we actually trained the SVR model on x and y, which were both scaled with two different scalars, x was scaled by SCX, I can show this to you again, X was scaled by SCX and Y was scaled by SCY. And so the consequence of this is that when you use the predict method on an observation, well, that observation has to be on the same scale as the values of your matrix of features on which your model was trained. So here, the first thing we have to do is apply the transformation, apply the scaling to that particular value. And how do we do this? Well, that's very easy. We have to call our scalar object for X, SCX, for the matrix of features X, and then from this object, apply the transform method, which will exactly feature scale this particular value. Put this particular value in the same scale that was applied to the whole matrix of features X. All right, so let's do this. That's the first thing we have to do here. We have to call our SC underscore X scalar object, for the matrix of features X, from which we're going to call the transform method, thank you Google Colab, which will take as input exactly this 2D array containing the single value 6.5. All right, I have to add a new one here, and there you go. So that's the first thing you had to do to make sure that your value here inside the predict method is scaled on the same scale that was used to scale the whole matrix of features X. All right, so that's the first thing, and therefore this will return your predicted salary, but in the scale that was applied to Y. The scaling that resulted from applying that second scalar object on the dependent variable vector Y. And therefore, instead of, getting here a salary around, let's say 160K, we will get a salary around this range of values. All right, and that's absolutely not what we want. It is still correct, but of course what we have to do now is reverse the scaling of Y, and more specifically of that prediction, of that predicted salary, in order to get the original scale of that prediction. And that's where you have to use this new method that can reverse the scaling, and which is called, I hope you found it on the internet or any documentation, this method is called the inverse transform method. And that's exactly what we have to apply here to indeed reverse the scaling, to go back to the original scale of Y, and therefore to go back to the original scale of that predicted salary. All right, so let's do this. In order to apply that inverse transform method, well, remember that any method has to be called from an object, and make sure to understand which object we have to call here. That's of course SCY, because we want to reverse the scaling that was used to transform the dependent variable vector Y. So here we have to call SC underscore Y, from which we're going to call that inverse transform method, thank you again Google Colab, which will take as input this whole prediction of the salary of the position level 6.5. And there you go, my friends. Now you have your prediction in the right scale. You want to check it out? Let's do this. We don't have to do a print here because this will return directly the prediction. I hope I didn't make any mistake with all these transform and inverse transform method and now all these parentheses, as you can see. But let's see. I just followed some logic here. And so now, if you're ready, well, let's execute our two cells here. First, this cell to indeed build and train the SVR model. So let's do this. And there we go. We get in the output the SVR model with all the parameters that were chosen. And we actually kept the default value for most of them, except that kernel parameter, for which we chose indeed the radial basis function kernel. And now, time to get the final prediction, the predicted salary for that position level 6.5, of course, from our SVR model. And to do this, we simply need to execute the cell to figure out that the predicted salary is in fact $170,000 per year. So that's once again a prediction that seems to make a lot of sense, based on what this person mentioned as a previous salary. I remind that in our little story, this person mentioned to have a 160K salary in the previous company characterized by this data. So not only it is very close, but also our predicted salary is higher than the requested salary. So that's all good for our negotiation. And to compare with our previous model, the polynomial regression model, well, remember that we had a 158K predicted salary and now we have a 170K. So anyway, both these models return a prediction that is indeed close to what would be the real salary of that position level number 6.5. And so once again, that shows that the SVR model is really well adapted to this data set, because indeed it can handle these nonlinear correlations between the position levels and the salaries. And we're going to see that much better in the visualization, because that's our next step, visualizing the SVR results in low resolution and high resolution. So that's what we'll do in this last tutorial. But now I really want to say congratulations, because you now know how to handle the not only transformations but also inverse transformations, and you can now return a prediction when some feature scaling was applied on both the matrix of features X and the dependent variable vector Y. It's really good that you know how to do this, because indeed in your future datasets and your future ML projects, you will definitely encounter this situation. So I'm really happy for you that you now have this extra tool in your machine learning toolkit. And now let's finish with the last exciting tutorial where we're going to visualize the results. So as soon as you're ready, let's observe the regression curve of the SVR model. And until then, enjoy machine learning. All right, are you ready for the final step? Visualizing the results of the SVR model. So we're going to basically do the same thing as what we did before, with the simple linear regression model and the polynomial regression model. And since we actually did it before, we're not going to do it all over again. The whole implementation of the code that plots the graph. Instead, I have a much better idea, which will actually be a great exercise for you to practice what was just explained before with this inverse transform method. So the idea I have in mind is to take the visualization code of the polynomial regression model, which is right at the bottom. Here it is. No, that's the linear regression model, and here it is, the polynomial regression result. So we're going to take this whole code here, and we're going to paste that inside a new code cell here for the SVR results. And now here we go. The exercise I would like you to do is to figure out what needs to be replaced in that code in order to make it work for the SVR. And really, I have explained everything. Let me actually zoom out a bit. Here it is. I have explained everything, with the transform methods and the inverse transform methods for you to be able to solve this problem. All right, so now please press pause on the video, and in a few seconds, we will implement the solution together. Okay. Let's do this. I hope you at least tried. What matters is that you try, to practice. And if you did not succeed, that's fine, because right now we're about to succeed together. All right, so let's do this. First, let's just replace the obvious change. We're going to replace polynomial here by support vector regression, or SVR, as you want. All right, and then let's take it line by line. This first line here is the line where we scatter plot, the different points of coordinates given by the position levels and the real salaries. So these red points here will be the real observations containing the real salaries for all the 10 different position levels. So here my question is, do we need to change anything? And the answer is, well, absolutely yes. Why is that? That's because we would like to have a nice chart with the original scales of both the values of our feature and the values of our dependent variable. And remember that both x and y were scaled with two different objects. X was scaled with the SCX scalar and y was scaled with the SCY scalar. So they are both on a certain scale, different than the original scale, which is this range of values. And therefore, now what we would like to do is, of course, to reverse the scale in order to scatter plot the points in their original scale. So very simply, we simply have to apply the inverse transform method here on both the matrix of features X and the dependent variable vector Y. So let's do this. That's our first step here. We're first going to call the SC underscore X scalar object, from which we're going to call the inverse transform method, which will take as input the whole matrix of features X. Perfect. And now let's do the same for y, which is still scaled with the scalar object SCY. So there you go. That's what we need to start with. SC underscore y, our scalar object for the dependent variable vector, and from which we have to call again the inverse transform method applied to that scaled vector y. Perfect, so now this will give us the points, the real points in their original scales. So that's good. And then we can keep the red color. That's all good. Perfect for the first line. Congratulations. Now let's move on to the regression curve. All right, so here the first obvious change is we will replace the name of the regressor. This was for the polynomial regressor, which we called linreg2, and now we called our SVR regressor. So we're quickly going to replace here linreg2 by regressor. First obvious change. Then a second obvious change is once again to remove all the polyreg, that was the actually transformation of the matrix of single feature into this matrix of powered features. So we have to remove all this actually. We're just going to keep X so far. And there you go. So now we have a clear line with just the predict method called from our regressor applied to the matrix of features X. And so now the question is, what do we need to do in order to get the regression curve back into the original scale? So try to figure it out. And now I'm going to give you the solution. Well, let's start with that coordinate, which is the x coordinates containing the position levels. Well, once again, x right now at this stage is still scaled with that scalar object SCX, and therefore we have to reverse the scaling here by applying once again the inverse transform method from our SCX object, and therefore I'm going to copy this because we're going to do exactly the same here. We're going to reverse the scale of x to find the original scale. All right, so all good for the x coordinates. And now a bit more difficult, the y coordinate, meaning the predicted salaries, right? This gave us the real salaries, and now we would like to have the predicted salaries on the regression curve of the SVR model. So according to you, what do we need to do here? And then this will actually be our final change, but yet not the easiest one. So please take a few seconds to think about this and try to make the right change. All right, so I'm going to give you the solution now. Well, let's take it step by step logically. First of all, predict x. What does it return? Well, it returns, indeed, the predicted salaries, but in the new scale of y. The new scale of the dependent variable vector. And here, be careful not to apply the SCX transform method. Here we had to apply it because this was the original scale of the feature, but here x is already scaled with that SCX scalar object, so we don't have to apply this transform method again. It's all good. So x is correct here, as the input of the predict method. But what is not correct is the scale of that predicted salary. Because indeed, as we just said, the predict method will return the prediction in the same scale as the one that was used in the training. And therefore, here we need to reverse the scale of that predicted salary in order to find the original scale of the dependent variable having these values. All right, so the only thing we need to do here is to call our SC underscore Y object, from which we're going to call the inverse transform method, which will take as input all this, right? The inverse transform method will take as input the predicted salary, but in the same scale that was used for the training. And therefore we have to reverse that scaling in order to find the original scale of y. All right, you see the idea? We're going to check now that all this is correct. It's easy to get confused sometimes, but I think I followed the right logic here. So let's see. Let's execute the cell here, and here are the SVR results. Congratulations if you managed to do the exercise, and also if you try to do the exercise. And now congratulations for getting this graph showing indeed the regression curve of the SVR model. So now we're going to do the same to get the curve with the higher resolution, because I would like to make my comments on this curve. It is much nicer. So we're going to do the same here. You're going to do the same exercise with that code which plots that high resolution curve. So let's get it here. Here it is. So copying this and pasting it right here below in a new code cell. And now let's quickly replace everything. So here we're gonna replace polynomial by support vector regression. Then let's replace that obvious regressor by regressor. Good. And then let's get rid of polyreg here with the fit transform method and the parenthesis. And good. Now let's see what we have to replace. So first of all, we get the grid, the high density point in the x-axis, meaning that instead of having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we'll have 1, 1.1, 1.2, 1.3, up to 9, 9.1, 9.2, 9.3, 9.8, 9.9, 10, right? That's what we are creating here. But when doing this, the problem is that x here is once again in the scale after the transformation. Therefore here, naturally, we have to reverse that scale, directly inside this min function and max function. So here, let's quickly reverse that scale of x by calling our SCX object, from which we're going to call the inverse transform method, which takes as input indeed x. All right, and then same here, SC_x dot inverse transform method applied to x. And now we're good with the grid. The next step, well, since the grid is now fine, well, the reshape that we do here in order to get indeed all these high density points is fine. So we can move on directly to the scatter plot of the real points, with the real observations, meaning the position levels and the real salaries. And here, well, that's pretty obvious based on what we've just done here. Of course, x and y are in the new scale, resulting from standardization. And so here we have to, of course, reverse that scale first by calling the SCX object, from which we call the inverse transform method to reverse the scale of x, and then same we call the SCY object, from which we call the inverse transform method to reverse the scale of y. All right, so that's for our real observations, all good. And now let's quickly finish it with the little change we have to make here for the regression curve in high resolution, thanks to this grid here that we made on the x-axis. And so here, well, as we said, x grid is fine. It is already back into the right original scale, but our predictions here, the predict method is applied to x grid, which, as we've just said, is in the right original scale, and therefore we have to put it back into the scale that was used for the training. And that's why the little trick here was not to forget to apply this SC_x scalar object, from which we call the transform method, in order to put x grid back into the scale resulting from standardization. Otherwise, the predict method would return nonsense predictions. All right, so all this regressor.predict SCX transform x grid returns indeed the predicted salaries for all the dense points in the x-axis given by x grid, but it returns these predictions in the new scale of y, meaning the one resulting from standardization as well. So we have to do one final thing here, which is of course to reverse that scale, and to do this we have to call our SC_y object, from which we're going to call the inverse transform method applied to this whole prediction returned by the predict method applied to the transformed x grid. All right, so now it should be fine. Let's check it out. We're going to have a much nicer curve now thanks to the high density points. So let's, well, first hope I didn't make any mistake, but I think it's really fun to play with all these transform and inverse transform methods. If you're still a bit confused or overwhelmed by all this, I really recommend to try to do it again on your own, because we just have to follow a logical process by figuring out in which scale we are and which transformation we have to do, whether it is the direct transformation to scale or the inverse transformation to go back to the original scale. So you can totally do this the same on your own. I think it's actually pretty fun. And now let's play that cell in order to get, well, that beautiful regression curve of the support vector regression model in high resolution. And as we can see, once again, we see that the SVR is perfectly well adapted to this kind of data set, with nonlinear relationships, because indeed the predictions on this regression curve come very close to the real results, meaning the real salaries, except, of course, for that one. And that's good to know about the SVR. If you have, some kind of outlier, or, a point that is far from the majority of your other points, well, the support vector regression model won't catch that properly. All right, so it's very interesting to see. The polynomial regression model did amazing here. We had a nice prediction for this last salary, but remember that there was some overfitting because we chose a high degree. And so maybe here we have a better learning actually because there is less overfitting. But still, it's quite borderline. But that's okay because what we wanted after all was to get a good prediction for the salary of position level number 6.5, and that was very good for our negotiation, so we can be very satisfied of the results provided by the SVR model. And mostly the important thing to remember is that indeed the SVR model is great for actually most of the datasets, whether they are linear or non-linear, because remember, when you build your SVR model, you can actually choose a linear kernel or a non-linear kernel. And if you choose a linear kernel, well, you will get amazing results on a dataset with linear relationships. And if you get a nonlinear kernel like the radial basis function or the polynomial kernel, you will get, again, amazing results on datasets with nonlinear relationships. Here we have some polynomial relationships between the salary and the position level. All right, so the SVR is an amazing model, but just be careful of the outliers, which are not caught well by the SVR model. In some datasets it's fine, but in some other problems, outliers can be important because they can reveal important insight. All right, so congratulations again. Now we're going to move on to the next section. So for R lovers who also want to learn R, well, join me in the R tutorials to learn how to implement the SVR model in R. And for those who only work on Python, well, join me in the next practical activity where we're going to build together a decision tree regression model. I can't wait to move on to this new model, and until then, enjoy machine learning.
Hello and welcome to this R tutorial. So today we're going to implement our second nonlinear regression model. It's going to be the SVR support vector for regression. So let's do it. We're going to use our regression template, and you're going to see how it's going to be so easy. So let's start by doing the basics. Set the right folder as working directory. So we'll go to Machine Learning AZ, Part 2 Regression, and then Support Vector Regression. Right, that's the right folder, position salary CSV file, all good. Let's click on Set as working directory to set the folder as working directory. Great, and now we can start. So we're going to take our regression template, and we're going to take everything from here to here, copy, and paste it in our SVR model. Here we go, and now we just need to change a few things. So let's start by changing the basics. We're going to replace regression model here by SVR. Okay, and same here, SVR results. Okay, and same here. All right, that was the easy step. And now let's get to the interesting step. So this interesting step is, of course, to create our SVR regressor. And we are creating it here. So I'm going to remove this. And now let's create this regressor. It's going to take 3 or 4 lines as usual. It's going to be very simple. We're going to use a function, which is the SVM function, very simply, because the SVR, is a support vector machine algorithm, but for regression. That's why we call it SVR. And therefore, we're just taking it from the SVM function, and you will understand why perfectly. So first, let's import the required package, because this function is contained in a package, which is the E1071 package. So let's go to our packages here, and let's check if we have it. So I have it because, of course, I used it before, but you might not have it. So in case you don't have it, I'm going to type this line here that you will need to execute to install this package. So you type install that packages here, and then in the parentheses and in quotes, you type the name of the package, which is E1071. All right, and then you just select this line and execute, and this will install the package. I'm not going to do it because mine is already installed, and therefore I'm going to put that in comment. I just pressed Command plus Shift plus C. All right. And now let's actually also add this line, library, and in parentheses, E1071, not in quotes. And this will select automatically the package here, E1071, because this will not always be selected. But by including that in your script, you will be all fine. This will always be selected. Okay? And now let's start creating our SVR regressor. So as usual, we're going to start by defining our regressor regressor, and then equals. And then, as I mentioned before, we're going to use the SVM function, which is actually this, and then in parentheses. And now let's press here F1 to have a look at the arguments and see what we need to input. So the first argument is formula. So you start to know perfectly what it is. Of course, the formula is our dependent variable, which is, remember, salary, and then tilde. I just pressed Alt N, and then a dot here. And the dot specifies that we are taking all the independent variable of our data set. We actually have one independent variable, which is the level independent variable. So we could also type here level, but most of the time we use the dot because, of course, we have a lot more than one independent variable. But as a reminder, I'm taking one independent variable here so that we can clearly see the visual graphic results of the different nonlinear models that we're building. Okay, so now let's add the second argument. So I'm adding a comma here and then next argument. So the next argument is data. Okay, I guess you know what this data argument will be. It's going to be, of course, our data set. Data set here because we did not create any training set or test set. You know, before we used the training set here as the data, but here we don't have any training set. So of course we're going to take the whole data set because we want to make very accurate predictions. Okay, and now finally, most important argument. Well, all the arguments are important, but the most relevant for this section about SVR is actually the next argument we are about to input. So this argument is actually not X or Y, these are optional arguments. The most important argument I was just talking about is this one, the type. Because this argument type will actually specify if you're making an SVM model, which is used for classification, or an SVR model, which is used for regression. So here, since we're building a nonlinear regression model, we will choose the EPS regression type. We could choose actually EPS regression or new regression, but as you can see, we want to take the most common one, the EPS regression. And if we were making a SVM model for classification, then we would have chosen C classification here. As you can see, C classification is the default type for classification. So in short, if you want to do regression, you choose type equals EPS regression. And if you want to do classification, you choose type equals C classification. And actually, in the next part about classification, we will make an SVM model. And for this specific model, we will choose the C classification type. Okay, but here we are doing regression, so we choose the EPS regression type. So let's input it. I'm going to type here type equals EPS regression. All right, and you need to put that in quote, actually. Don't forget the quotes to prevent any error from happening. Okay, and that's actually the final argument. If you want, we can add the kernel argument here, just to specify that we want the Gaussian kernel, because here we're using a Gaussian kernel, but it's the kernel selected by default here, so we don't actually need to input it. But just keep that in mind that we are here using the Gaussian kernel for our SVR model. Okay, but here we're all fine, and actually our model is ready to be created. So actually this is all we had to change in this regression template, and now we are ready to execute the sections one by one to create our model and find out about the final result and the final verdict, whether it's truth or bluff. So let's do it. I'm going to import the dataset first. All right, here we go, well imported, we can have a look. So these are our dataset with the levels as the independent variable and the salaries as the dependent variable. Okay, great. And no need to split the dataset into the training set and the test set. No need for feature scaling because we're using the very popular E1071 library that includes it. And now let's create our model. So I'm going to select this whole section here, press Command and Control plus Enter to execute. Done, regressor created. Great. And now let's predict the new result. Would you like to start by visualizing the SVR results first or predicting the new result? Well, let's actually predict the result because this is the most exciting step, and let's keep the best for the end. But this step is actually very exciting also because we're getting the final prediction, we're getting the final predicted salary. So, you know, it's as you want. If you're doing actually this code by yourself before me, that's actually a very good exercise. So I really encourage you to do this. Choose whatever you want to execute first. It's ready anyway. You don't need to change anything more now. So I'm going to execute that right now. and actually we obtain a predicted salary of $177,000. Great. So remember, this employee who we are negotiating the future salary right now said that its previous salary was 160K, and our model predicted that its previous salary was 177K. So first of all, that's actually close to what this employee said, and besides, it's on the good side of the negotiation, so that's actually pretty good, and we can be satisfied with this result and our model. But to be really satisfied, let's see what's happening with the graphic results. So I'm going to execute this section, and let's have a look at the SVR model. And here it is. I'm going to zoom on it, and better. Okay, so first of all, this model fits very well most of the data points. As a reminder, the real observation points are the red points here, and all the points in this blue curve here, which is the SVR model itself, are the prediction points. So for example, if we're taking this red observation point here, well, the prediction is perfect because the prediction point is the projection of this red point on the blue curve. So it's actually the red point itself because the red point is on the blue curve. So that makes a perfect prediction. But here, for example, if we take a less accurate prediction but still a very good one, then we take the real observation point here, the red point, we project it on the blue curve, and that's the difference between the real salary and the predicted salary, which is here, if we project it back on the y-axis, which contains the salaries. But you can see that for all of these points from this one to actually this one, the blue curve is actually getting very close to the real observation points, the red points, and so the predictions are very close to the real results. But that's for all these points of the data set, except for this one here. This one is left alone, which, by the way, corresponds to the CEO. So I'm sorry for the CEO, but the reason for what is happening here is that this is actually an outlier. Not to call the CEO an outlier, but this is an outlier because, as you can see, this point is actually far from the other points in terms of salaries. The CEO has a much higher salary than the previous positions. So for the SVR model, that's an outlier. And therefore, he actually didn't consider it. It's like it excluded this point in the model by not looking at it and making its predictions on these points here. So that's specifically due to the SVR algorithm itself, but there are a lot of parameters, and you can actually play with the parameters to change the way the SVR model perceives outliers. So for example, these parameters are the penalty parameters, the regularization parameters. It's most of the time well described in the description, and of course the E1071 library includes such techniques. But we're not going to do it here in this tutorial because we actually don't need to get a good prediction of the CEO salary. And remember, what we actually needed was a good prediction of the previous salary of this employee we're negotiating with. And this employee has a level 6.5. And around this point, we can see that the SVR model fits very well to our data set. And we actually get a prediction of 177K, quite close to the real or the mentioned salary of this employee, which is 160K. So that's actually pretty good, and therefore the verdict of truth or bluff according to our SVR model is rather truth. Okay, so not bad. The SVR made a good job here. Now let's see how decision tree regression and random forest regression will do. We'll see that in the next sections. So I'll see you there, and until then, enjoy machine learning.